What if everything we've ever assumed about space, about the very fabric of reality, isn't just incomplete, but fundamentally wrong? Picture this. The universe as we know it might be a tiny fraction of something far stranger, a cosmic illusion hiding truths so bizarre they defy imagination. This isn't science fiction, it's the frontier of modern astrophysics, where theories about the nature of space stretch the limits of human understanding. And today, we're diving into 30 of the most mind-bending ideas that could rewrite the rules of existence itself. Think about the night sky for a moment, those countless stars, galaxies, and voids that seem infinite. But what if that infinity is just a layer, a single slice of a multiverse where alternate realities collide? Or consider the possibility that black holes aren't just cosmic vacuum cleaners but gateways to other dimensions, or even the seeds of new universes. These aren't wild guesses, they're serious hypotheses backed by equations and observations proposed by some of the brightest minds in science. The deeper we look, the more the universe seems to unravel into questions rather than answers. That's the thrill of exploring these theories. Each one is a doorway to a reality more extraordinary than the last. From the holographic principle, suggesting our entire universe might be a two-dimensional projection, to the idea that time itself could be an illusion, we're about to journey through concepts that challenge everything we take for granted. This video isn't just a list, it's an invitation to see the cosmos through the eyes of pioneers who dare to imagine the impossible. So buckle up, because by the end, you might never look at space the same way again. What if the vivid three-dimensional world around us, the depth of mountains, the vastness of galaxies, even the sensation of moving through space, was nothing more than an illusion? That's the startling premise of the holographic universe theory, which proposes our reality might be a cosmic projection, a shimmering mirage encoded on a distant two-dimensional surface. Imagine the universe as a gigantic movie screen, where every event, every particle, every law of physics is just a flat image playing out for us in 3 dimensions. This isn't a metaphor, it's a serious mathematical framework with roots in one of physics' most profound discoveries, black holes. The idea gained traction through the work of physicist Leonard Susskind and others, inspired by a paradox involving black holes and information. When matter falls into a black hole, does it vanish forever, erasing information, something quantum mechanics strictly forbids? Susskind and Gerard T. Hooft proposed a radical solution. What if all the information swallowed by a black hole isn't lost but smeared across its event horizon, like data etched onto a celestial hard drive? This led to the holographic principle, suggesting that the entire universe might operate the same way, with our 3D reality written on a 2D boundary at the edge of space. The mathematics behind this comes from something called the AD/CFT correspondence, a theoretical bridge between two seemingly unrelated realms, gravity in a warped higher dimensional space and quantum field theory on its lower dimensional boundary. It's like discovering that a novel and its movie adaptation, despite different formats, tell the same story. If true, this means the universe could be storing information far more efficiently than we ever imagined, with every event in our 3D world corresponding to a pixel on a vast cosmic canvas. But the implications go even deeper. If spacetime is holographic, then gravity itself might not be a fundamental force but an emergent phenomenon, like how temperature arises from the motion of particles. Black holes could be the keys to unlocking this mystery, their event horizons acting as the ultimate information storage devices, encoding the past, present, and future of everything within them. Suddenly, the fabric of reality feels less like a fixed stage and more like a dynamic, fluid projection, where the very nature of space and time is negotiable. This theory doesn't just challenge our intuition, it redefines what physics could become. If the universe is a hologram, then the search for quantum gravity, the elusive theory uniting Einstein's relativity with quantum mechanics might need to start from an entirely new perspective. It suggests that the answers to the cosmos' biggest questions aren't hidden in the stars but in the invisible, lower-dimensional code underlying everything. And if that's true, reality as we know it might be the grandest illusion of all. Now imagine this: what if the universe wasn't just a hologram but something even more astonishing? An artificial simulation meticulously coded by an advanced civilization. The simulation hypothesis takes the idea of cosmic illusions to another level, proposing that everything we perceive, the stars, the laws of physics, even our own consciousness, might be nothing more than lines of code in an unfathomably sophisticated program. It sounds like science fiction, but some of the brightest minds in philosophy and physics have seriously entertained the possibility. The argument gained mainstream attention with philosopher Nick Bostrom's trilemma, which lays out three stark possibilities. Either nearly all civilizations at our level of technological development go extinct before reaching post-human capabilities, or advanced civilizations universally lose interest in creating ancestor simulations, or we are almost certainly living in one right now. Bostrom's reasoning hinges on one chilling assumption: if future civilizations could run countless simulations of their ancestors, the odds that we're in base reality become vanishingly small. It's like waking up in a room with a million identical doors and assuming yours is the only real one. Technological arguments add weight to the idea. If computing power continues to grow at its current exponential rate, a civilization even a few thousand years ahead of us could harness enough processing capacity to simulate entire universes down to the quantum level. Think of how video games have evolved from pixelated blips to hyper-realistic virtual worlds in just a few decades. Now extrapolate that progress over millennia. The boundary between real and simulated might eventually blur into irrelevance, but how would we even know? Some theorists suggest looking for cosmic glitches, tiny anomalies in the fabric of reality that could hint at underlying programming. Maybe the universe has a resolution limit, a pixelation effect hidden in the fine structure of space-time, or perhaps quantum indeterminacy, the way particles behave unpredictably until observed, isn't a fundamental law but an optimization trick, the simulation conserving resources by only rendering details when necessary. Even déjà vu could be explained as a system hiccup, a momentary blip in the code. Of course, not everyone buys into the simulation hypothesis. Critics argue that it's an untestable idea, more philosophy than science, a modern twist on age-old solipsism. Others point out the staggering energy requirements needed to simulate every conscious mind in history, making the whole proposition impractical. And then there's the existential kicker. If we're just characters in someone else's simulation, does that make our discoveries, our emotions, any less real? Whether you find the idea thrilling or unsettling, the simulation hypothesis forces us to confront profound questions about reality, free will, and the nature of existence itself. It's not just a theory about the universe, it's a mirror, reflecting our deepest hopes and fears about where we stand in the cosmic order. And if we ever do find proof, the greatest discovery in human history might come with the ultimate existential plot twist. The notion that our universe might be one of countless others, each with its own unique laws of physics, constants, and even dimensions, isn't just speculative fantasy. It's a concrete prediction of cosmic inflation, the leading theory for how the early universe expanded exponentially in a fraction of a second after the Big Bang. Picture this: if inflation never truly ended but instead continues eternally in distant regions of space, then new universes could be bubbling into existence endlessly like an infinite cosmic foam. This is the level I multiverse, where every possible variation of reality plays out somewhere in an unfathomably vast ensemble. Alan Guth, the physicist who first proposed inflation, realized something startling. When space expands faster than light, it doesn't just stretch the universe, it creates pockets where inflation stops randomly, each giving birth to a separate universe. Think of it like a boiling pot of water where steam bubbles form at different spots. Each bubble represents a universe cooling into its own distinct state, with its own version of particles, forces, and perhaps even time. These universes aren't just far away, they're forever beyond our cosmic horizon, receding faster than light could ever bridge the gap. What makes this theory so compelling is that it solves one of cosmology's biggest puzzles: why our universe seems so finely tuned for life. If there are infinite universes with different physical constants, then statistically, some will inevitably have the right conditions for stars, planets, and consciousness. We're not special, we're just lucky enough to exist in one of the rare universes where life is possible. The evidence for this wild idea might be hidden in the cosmic microwave background, the afterglow of the Big Bang. Tiny fluctuations in this radiation could carry imprints of collisions between our universe and neighboring bubbles, cosmic bruises left by encounters with other realities. While we've yet to find definitive proof, the math checks out and the implications are staggering. If eternal inflation is real, then the cosmos isn't just vast, it's an endlessly regenerating fractal of realities, each a closed-off experiment in physics. But here's the catch: we'll never see these other universes directly. The space between them inflates too quickly for light or any signal to cross. They exist in a realm forever out of reach, making the multiverse as much a philosophical provocation as a scientific one. Do unobservable universes even count as real? Some argue they're untestable, pushing the boundaries of science into metaphysics. Others counter that their existence is the most elegant explanation for our universe's peculiar fine-tuning. Either way, the inflationary multiverse forces us to confront a humbling truth. Our universe might just be a tiny island in an ocean of other worlds, each with its own version of history, its own laws, its own untold stories. And if that's the case, reality is far stranger and far richer than we ever imagined. The multiverse doesn't end with cosmic inflation. String theory takes the idea even further, proposing a dizzying landscape of universes where the laws of physics themselves aren't just different but exist in every mathematically possible variation. Imagine a cosmic library so vast it contains not just every book ever written but every book that could be written, with each volume representing a universe governed by its own unique set of rules. This is the level Roman II multiverse, a consequence of string theory's most startling prediction. There may be 10 to the power of 500 distinct ways for a universe to exist. At the heart of this idea is the concept of vacuum states, different configurations of spacetime and energy that could emerge from string theory's equations. Think of these states like valleys in an endless mountain range, each valley representing a stable universe with its own particles, forces, and constants. Some valleys might have gravity so weak it can't hold galaxies together. Others might have a cosmological constant so strong that stars never form. Our universe, with its delicate balance allowing for life, would be just one accidental dip in an inconceivably vast terrain. This is where the anthropic principle comes into play. If countless universes exist with every possible set of physical laws, it's no surprise we find ourselves in one where conditions permit our existence. It's like winning the cosmic lottery, not because the odds were in our favor, but because we couldn't have ended up anywhere else. Critics argue this reasoning feels circular, but proponents like physicist Brian Greene counter that it's no different from acknowledging we live on a planet with liquid water and breathable air. The universe isn't fine-tuned for us, we're the accidental beneficiaries of its untuned randomness. String theory's landscape multiverse raises thorny questions about falsifiability. How do you test a theory that posits an infinite array of unobservable universes? some researchers suggest looking for indirect evidence, like signatures of collisions with other universes in the cosmic microwave background or anomalies in the distribution of dark matter. Others argue the multiverse is more metaphysics than physics, a tantalizing idea that may forever linger beyond the reach of experiment, yet the sheer imaginative power of the concept keeps it alive. Green's elegant analogies comparing the multiverse to a cosmic quilt or a reality generator have brought the idea into popular culture, transforming abstract equations into visceral possibilities. Whether it's ultimately proven or discarded, the level Roman II multiverse forces us to reckon with a profound truth. The laws we consider fundamental might not be universal at all, just a quirky local ordinance in an infinite cosmic metropolis. And if that's the case, the search for a theory of everything might need to embrace a far stranger reality than we ever expected. What if every choice you've ever made, every tiny decision, every random quantum event didn't just play out one way but spawned entirely new universes, each branching off to explore every possible outcome? This is the mind-bending core of the many worlds interpretation of quantum mechanics, a vision of reality where the cosmos constantly fractures into countless parallel timelines, each as real as our own. Unlike the inflationary or string theory multiverses, which imagine distant realms with different laws of physics, the many worlds multiverse suggests that every quantum possibility you didn't experience is unfolding right now in a reality just as tangible as this one. The idea traces back to Hugh Everett, a young physicist who, in the 1950s, dared to challenge the dominant Copenhagen interpretation of quantum mechanics. While Copenhagen insists that particles exist in probabilistic superpositions like Schrödinger's infamous cat, simultaneously alive and dead until measured, Everett proposed something far more radical. Those superpositions never collapse. Instead, the universe splits, with one version of reality where the cat lives and another where it dies, both equally real but forever separated by the branching flow of quantum events. There's no mysterious observer effect needed, just the cold, deterministic machinery of wave functions evolving endlessly, spawning new worlds with every interaction. But how does this branching actually happen? The key lies in a phenomenon called quantum decoherence. Imagine tossing a pebble into a still pond. The ripples spread out, interacting with the environment in complex ways. In quantum terms, when a particle's wave function encounters its surroundings, whether it's a measuring device or just the air molecules around it, its superposition leaks into the environment, creating correlations that effectively lock in one outcome for each branch. From our perspective inside a single branch, it looks like randomness, like the dice of the universe landing on one number. But zoom out, and every possible roll is happening somewhere in some universe. Critics argue this seems extravagantly wasteful. Why should reality multiply itself endlessly just to avoid wave function collapse? But proponents point out that many worlds eliminates the need for arbitrary dividing lines between the quantum and classical worlds, a problem that's haunted the Copenhagen interpretation for decades. There's no special moment when observation magically resolves a superposition. The math just keeps flowing, worlds splitting silently like tributaries in an ever-widening river. The implications are staggering. Every time you flip a coin, the universe divides, one where it lands heads, another where it's tails. Every quantum fluctuation in a star, every random mutation in DNA, every choice you didn't make spawns new realities. Somewhere, dinosaurs still roam Earth because the asteroid missed. Somewhere, you took that job offer you declined. Somewhere, Schrödinger's cat is both definitively alive and definitively dead, each version unaware of the other. Modern developments have only deepened the theory's reach. Cosmologists like Max Tegmark argue that many worlds isn't just about quantum mechanics, it's a fundamental feature of reality, with branching timelines explaining everything from the arrow of time to the nature of consciousness. Others propose that these parallel worlds might one day be detectable through subtle quantum signatures, though for now they remain tantalizingly out of reach. Whether you find the idea liberating or unsettling, the many worlds interpretation forces us to confront a profound truth. Reality might not be a single, linear story, but an infinite tapestry of alternate plots, each thread as real as the next. And if that's the case, the version of you reading this script is just one note in a cosmic symphony playing every possible melody at once. Max Tegmark's mathematical multiverse takes the idea of parallel realities to its most extreme and abstract conclusion. What if every possible mathematical structure isn't just a description of reality, but is reality itself? This is the Level 4 multiverse, a cosmos where the fabric of existence isn't made of particles or forces, but of pure mathematics. No stars, no atoms, no space-time, just equations and their solutions, each manifesting as a self-contained universe with its own rules. It's a dizzying concept, one that challenges not just our intuition but the very definition of what real means. Tegmark's argument hinges on a peculiar observation scientists have pondered for centuries: the unreasonable effectiveness of mathematics. Why do the laws of physics, from the motion of planets to the behavior of quantum particles, adhere so precisely to mathematical principles? Einstein called it a mystery, and Nobel laureate Eugene Wigner wondered if it was a gift we neither deserved nor understood. Tegmark's answer is radical: mathematics isn't just a tool for describing reality, it is reality. In this view, our universe isn't described by equations, it's an equation, one of infinitely many, shut up and calculate structures humming along in an abstract mathematical landscape. Imagine a library containing not just every book ever written, but every possible arrangement of words, whether coherent or nonsensical. Most would be gibberish, but somewhere in that infinite stack, you'd find Shakespeare's works, every scientific paper, even a perfect biography of your life. Tegmark's multiverse works the same way. Most mathematical structures might be chaotic or inert, but some contain self-aware substructures like us, experiencing what we call physics from the inside. Our universe, with its elegant symmetries and predictable laws, isn't special. It's just one of the rare structures complex enough to host observers. Critics argue this idea veers into metaphysics. How could a universe with no physical substrate, just abstract relations, give rise to something as visceral as consciousness? Some physicists, like Sabine Hossenfelder, dismiss it as untestable, a philosophical dead end that can't be falsified. Others counter that Tegmark's framework isn't just speculative, it's a natural extension of the same reasoning that led us to accept other multiverse levels. If inflation predicts distant bubble universes and quantum mechanics suggests branching timelines, why couldn't mathematics itself be the ultimate generator of reality? The implications are staggering. If Tegmark is right, then the search for a theory of everything might not be about discovering fundamental laws, but about finding which mathematical structure we're embedded in. It suggests that the deepest truths of existence aren't written in the stars, but in the language of numbers, a language that might not care whether we understand it or not. And if that's true, reality isn't just stranger than we imagine. It's stranger than we can imagine, existing beyond space, time, or even physics as we know them. What if the relentless march of time, the feeling that moments slip inexorably from future to past, was nothing more than a trick of perception? The block universe theory shatters our intuitive sense of time's flow, proposing instead that past, present, and future exist simultaneously in a frozen four-dimensional tapestry. Picture reality as a vast loaf of bread, where each slice represents the entire universe at a single moment, stacked together into an unchanging block. In this view, your birth, your life, and even events yet to come are all equally real, fixed in place like frames in a cosmic film reel. This radical idea springs directly from Einstein's theory of relativity, which revealed that time isn't universal but elastic, stretching and compressing depending on motion and gravity. The relativity of simultaneity demonstrates that two events occurring at the same time for one observer might happen in sequence for another. For a spaceship racing near light speed, your morning coffee and a supernova in a distant galaxy could appear simultaneous, while to someone on Earth they're years apart. If now is subjective, then the division between past and future crumbles, leaving only a static network of events woven into spacetime's fabric. The implications upend everything we assume about existence. If the future is already out there, lurking in the block, does free will evaporate? Philosophers split into two camps. Eternalists argue that our choices are illusory. Every decision you'll ever make is just a coordinate in the block. But others counter that consciousness itself might be the key, with our subjective experience moving through the block like a spotlight scanning a film strip. In this view, free will isn't about changing the block, but about how we navigate its fixed contours. Consciousness adds another layer of mystery. Why do we perceive time's arrow at all if the universe is timeless? Some theorists link it to entropy, the universe's tendency toward disorder. Like an arrow shot from a bow, entropy gives time its direction, creating the narrative illusion of cause and effect. Others propose that consciousness stitches moments together, stitching a coherent now from the block's frozen threads. The block universe doesn't just challenge physics, it forces us to rethink what it means to exist. If all moments are equally real, then grief and anticipation take on new meaning. The loved ones you've lost aren't gone, their moments still shimmer in spacetime's weave. The future isn't empty potential but a landscape waiting to be explored. Reality might be less like a river and more like a sculpture, where every point in time is carved into the cosmos forever. And if that's true, the present moment isn't fleeting, it's simply where your consciousness happens to be standing in the grand gallery of eternity. The Big Bang isn't the only origin story for our universe. What if it was just the latest chapter in an endless cosmic cycle of death and rebirth? Enter the Big Bounce, a radical alternative where the universe doesn't begin with a singularity, but emerges from the ashes of a previous collapse, like a phoenix perpetually rising and falling in an infinite loop. This isn't just poetic imagery, it's a serious cosmological model that reimagines the fate of everything. Instead of expanding forever into cold emptiness or crunching into oblivion, the universe could be pulsing like a heartbeat, each contraction followed by a new expansion, a new Big Bang, a new universe born from the old. At the heart of this idea lies a cosmic escape clause, the singularity problem. Traditional Big Bang theory hits a wall when we rewind time to the very beginning. Gravity becomes infinitely strong, space-time curves into a mathematical paradox, and the laws of physics break down entirely. But quantum gravity, the long-sought theory marrying Einstein's relativity with quantum mechanics, might offer a way out. In the final moments of a collapsing universe, quantum effects could prevent total annihilation, creating a repulsive force that halts the crunch and triggers a rebound. Picture a rubber band stretched to its limit just before it snaps. Quantum jitters might send it recoiling outward, birthing a new cosmos from the remnants of the old. Evidence for this cyclical universe might be hidden in the faint whispers of the cosmic microwave background, the afterglow of the Big Bang. Strange anomalies in this radiation, like unexpected temperature fluctuations or large-scale patterns, could be echoes of a pre-bounce universe, faint scars left by collisions between long-dead galaxies in a prior cycle. Some researchers even speculate that the mysterious cold spot in the CMB, a vast region eerily devoid of heat, might be a relic of a previous universe's structure imprinted onto our own. It's as if the cosmos has a memory carrying traces of its past lives into each new iteration. Roger Penrose, the Nobel-winning physicist, took this idea even further with his conformal cyclic cosmology. In his model, the distant future of one universe becomes the Big Bang of the next, with infinity acting as a cosmic reset button. As black holes evaporate and particles lose mass over eons, the universe becomes indistinguishable from the featureless singularity of a new beginning. Time itself loses meaning at these extremes, allowing the end of one cycle to seamlessly morph into the start of another. Penrose claims to have found circular patterns in the CMB potential signatures of black hole collisions from a universe predating ours. While controversial, his work challenges us to rethink not just the origin of the cosmos, but its ultimate destiny. Critics argue the Big Bounce remains speculative, with quantum gravity still incomplete and no smoking gun evidence for cyclical universes. Others question whether entropy, the steady increase in disorder, would allow endless rebirths without degrading the universe's structure over time. Yet the theory's elegance is undeniable. It offers a vision of cosmic immortality, where existence isn't a one-time fluke but an eternal rhythm, an unbroken chain of universes, each inheriting the legacy of those before. Whether the Big Bounce is proven or not, it reminds us of a profound truth. The universe might not have a single beginning or end, but instead a story without finality, a saga written in the endless turning of time itself. What if the Big Bang wasn't the beginning of everything but the echo of a cosmic collapse in another reality? This provocative idea reframes our universe's birth as a side effect of a black hole's formation in a parent universe, a cosmic matryoshka doll where each universe births another from its darkest depths. At first glance, it sounds like science fiction, but the math behind it offers startling solutions to some of cosmology's biggest puzzles, from the singularity problem to the enigma of dark energy. Black holes are already cosmic paradoxes, regions where gravity crushes matter into an infinitely dense point, a singularity where physics as we know it stops making sense. But what happens to all that swallowed material? The traditional view assumes it's lost forever, but quantum mechanics insists information can't truly vanish. Here's the twist: when a black hole forms, its event horizon isn't just a one-way membrane. It might be the seed of a new space-time, erupting inward to create an entirely separate universe. Picture a funnel collapsing inward, only to balloon outward on the other side, a gravitational Big Bang where our entire cosmos emerges from the wreckage of a predecessor's collapse. This theory elegantly sidesteps the singularity problem. Instead of a mysterious, infinitely dense starting point, our universe begins with the finite, if unimaginably extreme conditions of a black hole's interior, a place governed by quantum gravity rather than classical physics breakdown. It also ties into the holographic principle, with the black hole's event horizon acting as a cosmic projector, encoding the information of the parent universe onto the fabric of the new one like a cosmic inheritance. Lee Smollen's cosmological natural selection takes this idea even further, proposing a Darwinian twist. Universes could evolve if each black hole spawns a new universe with slightly tweaked physical constants. Then over countless generations, universes that produce more black holes, more offspring, would dominate the multiverse landscape. Our universe's fine-tuned constants, like the strength of gravity or the mass of electrons, might not be random but the result of a cosmic selection pressure favoring black hole production. It's survival of the fittest on a scale so vast it redefines biology itself. Dark energy, the mysterious force accelerating the universe's expansion, might even find an explanation here. Some models suggest it's a residual effect of the parent universe's gravitational pull, an imprint left on our spacetime as it broke free from the black hole's grip. Like a child inheriting traits from a parent, our cosmos could carry echoes of its origin in the form of this enigmatic energy. Critics argue the theory is hard to test. How do we observe a universe that predates our own? But proponents point to subtle fingerprints. The cosmic microwave background might hold faint anomalies like unexpected temperature variations or polarization patterns that betray our universe's violent birth. Others suggest the total mass of our cosmos could align with predictions for a black hole's interior, a cosmic math problem waiting to be solved. Whether this theory holds or not, it reframes our place in the cosmos. We might not be the first universe, and we certainly won't be the last. Instead, we're part of an infinite lineage, a chain of cosmic rebirths where black holes aren't just destroyers but creators, weaving new realities from the ashes of the old. And if that's true, the night sky isn't just a window to space, it's a mirror, reflecting the hidden history of existence itself. The ekpyrotic universe theory throws our cosmic origins into an entirely new light, one where the Big Bang wasn't a spontaneous explosion of energy, but the aftermath of a violent collision between two higher-dimensional worlds. Picture our universe as a vast, floating sheet, a three-dimensional brain drifting through an 11-dimensional space. Nearby, another brain hovers, invisible to us but gravitationally entwined. When these membranes finally collide, the impact unleashes enough energy to forge an entire cosmos in a searing flash. This isn't just a wild hypothesis, it's a meticulous alternative to cosmic inflation, one that solves the same cosmological puzzles while rewriting the story of our beginnings. Unlike inflationary theory, which relies on a fleeting period of exponential expansion to explain the universe's smoothness and flatness, the ekpyrotic model achieves these features through a slow, graceful dance of the brains before their fateful crash. As the membranes draw near over eons, their mutual gravitational pull stretches and flattens them like dough being rolled thin, eliminating wrinkles and curvature. When they finally meet, the energy of impact is channeled perfectly homogeneously across the brain's surface, answering the horizon problem without needing faster-than-light expansion. It's as if the universe didn't require a sudden stretching to become uniform. It was born that way, sculpted by the pre-collision tension between the brains. The theory's elegance doesn't stop there. Inflation struggles to explain why the universe's initial energy density was so finely balanced, a mystery called the flatness problem. The ekpyrotic scenario sidesteps this entirely. The brain's gradual convergence naturally drives their geometry toward flatness, much like how two sheets of paper pressed together resist bending. By the time they collide, any curvature has been ironed out, leaving a universe that appears perfectly flat without improbable fine-tuning. But how could we ever test such an exotic idea? The answer might lie in gravitational waves, ripples in spacetime itself. Inflation predicts a particular spectrum of primordial gravitational waves, a cosmic fingerprint imprinted during the universe's rapid expansion. The ekpyrotic model, however, suggests a quieter signal. Brain collisions would generate waves too, but with a distinct frequency pattern. Current experiments like LIGO and future space-based detectors could, in principle, spot the difference. Some researchers even propose that anomalies in the cosmic microwave background, subtle swirls in the polarization of ancient light, might carry traces of the pre-collision brain dynamics, like shadows cast by a hidden higher-dimensional drama. Critics argue the theory introduces unnecessary complexity. Why invoke unseen brains and extra dimensions when inflation works well enough? Supporters counter that the ekpyrotic model eliminates inflationary headaches, like the multiverse's anything-goes randomness or the need for an inflated field with oddly fine-tuned properties. It also offers a tantalizing link to string theory, where brains are fundamental objects, not just speculative add-ons. Whether the ekpyrotic universe ultimately holds up or not, it forces cosmology to confront deeper questions about the nature of reality. Are we the product of a solitary quantum fluctuation or the scars of a higher dimensional collision? The answer might rewrite not just our origin story, but the very fabric of spacetime itself. If black holes are the universe's ultimate trash compactors, crushing matter into oblivion, then white holes are their bizarre cosmic opposites, theoretical fountains spraying out energy and matter instead of swallowing them. Imagine a celestial fire hydrant blasting particles into existence, a region of space-time where nothing can enter but everything must escape. While no white hole has ever been observed, they emerge naturally from Einstein's field equations as the time-reversed twins of black holes. Flip a black hole's gravitational collapse in reverse, and you get this explosive phenomenon. A singularity not pulling everything in but violently pushing everything out. The math here is just as elegant as it is strange. Einstein's equations don't care which direction time flows, they're symmetric. So if black holes exist, white holes should too, at least on paper. But why don't we see them? One possibility is that white holes are incredibly short-lived, exploding into existence and dissipating almost instantly like cosmic fireworks. Another, even wilder idea is that white holes aren't just theoretical oddities but could be hiding in plain sight as the very origin of our universe. This is where quantum gravity steps in, offering a potential bridge between white holes and the Big Bang. Carlo Rovelli, the physicist behind loop quantum gravity, proposes that when a black hole dies, it doesn't vanish into nothingness. Instead, quantum effects at its core could trigger a transformation, flipping it inside out to become a white hole. Picture a deflating balloon suddenly reinflating with explosive force, but on a cosmic scale. The mind-blowing implication: the Big Bang might not have been a singular, standalone event but the rebirth of a black hole from a prior universe, its crushing singularity inverted into a white hole's creative outburst. The numbers make this eerily plausible. A typical stellar black hole's evaporation, thanks to Hawking radiation, would take far longer than the current age of the universe. But loop quantum gravity suggests that at microscopic scales, spacetime is granular, woven from tiny quantum threads that resist infinite collapse. This granularity could cause a black hole's core to rebound before reaching a true singularity, birthing a white hole in a process lasting mere fractions of a second from an outside observer's perspective. From inside, however, the transformation could appear to take billions of years, meaning the white hole's explosion might unfold in slow motion relative to its parent black hole's timeline. If this is true, our universe could literally be the aftermath of a white hole explosion from another cosmos's black hole death. It's a cosmic Russian nesting doll where universes are born from the corpses of their predecessors. The echoes of this might even be detectable. Some theorists suggest the cosmic microwave background could contain imprints of this violent transition, anisotropies or patterns that don't quite fit standard Big Bang models. Others hunt for gamma-ray bursts with unusual signatures, potential white hole birth cries echoing across the cosmos. Of course, the idea isn't without skeptics. White holes violate the second law of thermodynamics by seemingly creating order from disorder, and no known process naturally produces them. Yet in the quantum realm, where particles pop in and out of existence and time can lose its arrow, the impossible starts to feel plausible. Whether white holes are real or not, they force us to confront a profound question. What if the universe isn't a one-time creation but part of an endless cycle of destruction and rebirth, where every ending is just another beginning in disguise? The silence of the cosmos is unsettling. After billions of stars, trillions of planets, and decades of listening, why haven't we found a single whisper of alien civilization? The Fermi Paradox looms over astronomy like a riddle wrapped in enigma. If life is statistically probable, where is everyone? The answers might be hiding in plain sight, buried in theories that redefine not just our search for aliens, but our understanding of the universe itself. Take the zoo hypothesis, the idea that advanced civilizations know we're here but deliberately avoid contact, treating Earth like a protected wildlife preserve. Picture humanity as an exhibit in a galactic museum, observed but not disturbed, left to evolve without interference. This isn't just sci-fi speculation. It's a serious response to the paradox, suggesting that interstellar societies might follow ethical protocols akin to Star Trek's Prime Directive. The chilling implication: we're not alone, we're isolated by design, like animals in a cage unaware of the zookeepers watching from beyond the bars. Then there's the dark forest theory, a far more sinister explanation rooted in game theory. Imagine the universe as a vast, shadowy woodland where every civilization is a hidden hunter, terrified of revealing its location. Broadcasting signals or expanding aggressively could invite annihilation from paranoid neighbors, preemptively eliminating potential threats. In this cosmic Darwinism, silence isn't strange, it's survival. The theory draws from humanity's own history. When cultures with uneven technology collide, the results are rarely peaceful. If even one civilization acts this way, the entire galaxy could be forced into silence, a stalemate of mutual suspicion spanning light years. But what if the answer isn't alien behavior, but cosmic geography? We might be floating in a galactic void, a sparse neighborhood where intelligent life is exceptionally rare. The universe isn't uniformly dense. Filaments of galaxies weave through enormous empty regions called voids. If Earth lies in one, the nearest civilizations could be impossibly distant, their signals too faint to detect. It's like living in a desert while the rest of the galaxy thrives in bustling cities. We're not being ignored, we're just stranded in the sticks of the Milky Way. These theories force us to confront uncomfortable truths. If the zoo hypothesis is real, our attempts at communication might be futile, even naive. The dark forest suggests that shouting into the void could be catastrophic, turning SETI efforts from hopeful to reckless. And if we're truly alone in a void, the universe might be far lonelier than we imagined. Each possibility reshapes how we view our place in the cosmos. Are we the protected, the prey, or simply the isolated? Yet the paradox remains unresolved, a puzzle that says as much about us as it does about aliens. Our assumptions about intelligence, technology, and even morality might be hopelessly anthropomorphic, blinding us to realities we can't yet comprehend. The silence isn't just a mystery, it's a mirror reflecting our deepest fears and hopes about what or who might be out there. What if every thought you've ever had, every memory you cherish, every sensation of being alive wasn't the result of billions of years of cosmic evolution, but a fleeting glitch in the void? This is the unsettling premise of the Boltzmann brain, a thought experiment that turns our understanding of reality inside out. Named after physicist Ludwig Boltzmann, who pioneered statistical mechanics, the idea suggests that in an infinite universe governed by entropy, random fluctuations could spontaneously generate self-aware entities, brains floating in space, complete with false memories and imaginary worlds for just an instant before dissolving back into chaos. At its core, the paradox arises from thermodynamics. Over incomprehensible timescales, the universe tends toward disorder, but tiny pockets of order can still emerge by chance. Most of these fluctuations would be trivial, a brief alignment of particles, a momentary ripple in the void, but given enough time, even the most improbable events become inevitable. A fully formed brain, complete with fabricated experiences of a past and surroundings, is statistically unlikely, but in eternity, unlikely loses meaning. The shocking implication: you're far more likely to be one of these momentary aberrations than a product of 13.8 billion years of continuous cosmic history. The problem deepens when we consider the arrow of time. Entropy gives time its direction, explaining why we remember the past but not the future. But if Boltzmann brains can pop into existence with false memories of a past that never was, then entropy's arrow wobbles. Why does our universe have a clear past and future, rather than a chaos of disconnected moments where observers flicker in and out of existence? This isn't just philosophy, it's a crisis for cosmology. A theory that predicts we should be Boltzmann brains is a theory in serious trouble. Modern physics races to avoid this bizarre conclusion. Inflationary cosmology proposes that our universe's low entropy beginning wasn't random but the result of a specific mechanism, a quantum fluctuation in a pre-existing high-energy field. String theory's landscape multiverse suggests that while some universes might devolve into Boltzmann chaos, others like ours stabilize into orderly structures. Even quantum gravity gets involved, with some models proposing that spacetime's granularity at tiny scales prevents the kinds of fluctuations needed to spawn rogue consciousness. Yet the specter of the Boltzmann brain lingers, a reminder of how fragile our grasp on reality might be. It forces us to confront the limits of probability in an infinite cosmos where the improbable becomes inevitable. Are we the products of a grand cosmic narrative, or just statistical noise in an endless sea of randomness? The answer could redefine not just our place in the universe, but the nature of existence itself. Somewhere in the far future, the universe might not fade into cold darkness. It could be torn apart atom by atom in a violent cosmic crescendo known as the Big Rip. This isn't just another doomsday scenario. It's the ultimate fate of everything if dark energy, the mysterious force accelerating the universe's expansion, grows stronger over time. Picture the fabric of spacetime stretching faster and faster until it outstrips even the bonds holding matter together. Galaxies would be shredded first, then stars, planets, and eventually the very atoms composing your body, ripped into particles too far apart to ever interact again. Dark energy currently makes up 68% of the universe's energy budget, acting like an anti-gravity force pushing galaxies apart. But the Big Rip hinges on a specific type called phantom energy, which doesn't just accelerate expansion, it intensifies. If this exotic form exists, the universe's fate is sealed. Around 60 billion years from now, the Milky Way stars would vanish over the cosmic horizon as space expands faster than light can bridge the gap. With 2 months left, the solar system would fly apart. In the final 30 minutes, Earth itself would disintegrate, and in the last terrifying instance, atomic nuclei would be torn asunder, leaving nothing but a sea of isolated quarks drifting in an ever-widening void. Modified gravity theories offer a potential escape hatch. If Einstein's general relativity isn't the final word on gravity, if it breaks down on cosmic scales, then dark energy might not need to exist at all. Theories like modified Newtonian dynamics tweak gravity's behavior to explain galactic rotation without invoking dark matter, and some extensions aim to do the same for dark energy. These models suggest that what we perceive as accelerating expansion could be an illusion caused by gravity weakening differently over vast distances. If correct, the Big Rip might vanish from the forecast, replaced by a gentler, if still inevitable, heat death. Observations are tightening the noose around these possibilities. The Dark Energy Survey and measurements of baryon acoustic oscillations, frozen echoes of the early universe's sound waves, have constrained phantom energy's wiggle room. So far, the data favors a less extreme form of dark energy, one that would leave galaxies drifting apart but intact, but the uncertainty is still vast. Future telescopes like the Vera Rubin Observatory could detect subtle changes in expansion rates over billions of years, revealing whether dark energy is constant or growing, and whether the phantom is real. The Big Rip isn't just about how the universe ends, it's a mirror reflecting our deepest uncertainties. We've mapped the cosmos with staggering precision, yet 70% of its energy remains a shadow. Whether the universe meets a violent or quiet end hinges on forces we've yet to understand, forces that might rewrite physics itself before the final curtain falls. What if the universe isn't a one-time accident but part of an endless cycle of birth, death, and rebirth, a cosmic evolutionary chain where black holes act as seeds for new realities? This is the heart of cosmological natural selection, a radical theory proposing that universes don't just exist, they evolve, adapting over generations like living organisms. At the center of this idea lies a breathtaking twist. Every black hole might be a gateway to a new cosmos, each with subtly tweaked physical constants, creating a Darwinian playground where only the most fit universes survive. Think of it like a vast cosmic family tree. When a black hole forms, its crushing singularity doesn't just vanish into oblivion. According to physicist Lee Smolin, the extreme conditions inside could trigger a quantum rebound, birthing an entirely new universe in the process. But here's the kicker. The laws of physics in that new universe wouldn't be identical to its parents. Small variations, like the strength of gravity or the mass of electrons, might shift randomly, just as genetic mutations alter biological traits. Over countless generations, universes that produce more black holes, more offspring, would dominate the multiverse, while those with infertile physics fade into obscurity. This elegantly explains one of science's greatest mysteries: why our universe seems so finely tuned for life. If gravity were slightly stronger, stars would burn out too quickly. If the cosmological constant were larger, galaxies couldn't form. Cosmological natural selection offers a simple answer. We live in a universe optimized for black hole production, not life. The conditions that allow for stars, planets, and ultimately us are mere side effects of a deeper evolutionary pressure. It's survival of the fittest on a scale so vast it redefines biology itself. The implications ripple outward. If true, our cosmos isn't a static stage but a link in an infinite chain, shaped by the same principles that mold species on Earth. Black holes aren't just destructive monsters but cosmic midwives, birthing new realities with every collapse. Even the enigmatic dark energy accelerating our universe's expansion might not be random. It could be an evolutionary adaptation, a tweak that maximizes black hole formation over trillions of years. Critics argue the theory is hard to test. How do you observe a universe that existed before your own? Yet tantalizing clues might lurk in the shadows. If black holes are cosmic reproducers, their statistical properties like size, distributions, or merger rates could reveal patterns suggestive of evolutionary pressure. Some researchers even propose that anomalies in the cosmic microwave background, the faint glow of the Big Bang, might carry echoes of our universe's parent, like genetic markers in a celestial ancestry test. Whether cosmological natural selection holds up or not, it forces us to rethink the universe as something dynamic, malleable, almost alive. The night sky might not just be a static canvas of stars but a snapshot of an eternal evolutionary process where every black hole is a promise of new worlds to come. And if that's true, we're not just inhabitants of the cosmos, we're witnesses to its relentless, unfolding story. Black holes aren't just cosmic vacuum cleaners, they're information shredders, seemingly annihilating the very blueprint of reality itself. Here's the problem. Quantum mechanics insists that information can never truly be lost. Every particle, every interaction, leaves an indelible mark on the universe's ledger. Yet black holes, with their insatiable appetites, appear to break this rule, swallowing stars, planets, and light without leaving a trace of what went in. This contradiction, known as the information paradox, has haunted physicists for decades, threatening to unravel our understanding of reality at its core. Stephen Hawking first exposed the paradox in the 1970s when he discovered black holes aren't entirely black. They emit radiation, now called Hawking radiation, slowly leaking energy and fading away over eons. But here's the catch. This radiation seems random, carrying no imprint of the matter that fell in. It's like burning a library and claiming the smoke particles contain no trace of the book's contents. If the radiation holds no information, then when the black hole finally vanishes, the information it consumed vanishes too, a direct violation of quantum mechanics' sacred principle of unitarity, which demands that information must always be preserved, never destroyed. The debate spiraled into crisis with the firewall paradox. In 2012, a team of physicists proposed a nightmarish scenario. If information somehow escapes a black hole, the event horizon, the point of no return, must transform into a searing wall of high-energy particles, incinerating anything crossing it. This directly contradicts Einstein's general relativity, which predicts an observer falling into a black hole would notice nothing unusual at the horizon. So which is it, a fiery death or a smooth descent? The answer could determine whether relativity or quantum mechanics holds the deeper truth about spacetime. Recent breakthroughs in holography have reignited hope for a solution. The holographic principle suggests that all the information swallowed by a black hole isn't stored in its depths but encoded on its event horizon like a cosmic hard drive. Calculations of holographic entropy, a measure of this information, show that the horizon's surface area, not the black hole's volume, determines its information capacity. This aligns with the idea that our three-dimensional universe might be a projection of data written on a two-dimensional boundary, with black holes as extreme case studies. Even more tantalizing are hints that Hawking radiation might not be random after all. Advanced models suggest subtle quantum entanglement between particles inside and outside the black hole could preserve information, weaving it into the radiation like invisible ink. If true, the paradox crumbles, information escapes not in the smoke but in the pattern of the smoke. Experiments with analog black holes in labs, using sound waves or light to mimic event horizons, are now testing these ideas, probing whether information really can cheat cosmic destruction. Why does this matter? Because if information can vanish without a trace, the bedrock of physics fractures. Every prediction, from the fate of stars to the nature of time, relies on information's permanence. Solve the paradox, and we might finally glimpse the quantum code underlying spacetime itself. Fail, and reality could be far stranger and far less predictable than we ever imagined. The universe keeps its secrets well, but black holes, those darkest of enigmas, might just be the keys to unlocking them. Imagine if every time two particles became entangled, their fates mysteriously linked across vast distances. They weren't just communicating faster than light, but were secretly tied together by a hidden bridge through spacetime itself. This is the bold claim of the ER=EPR conjecture, a theory so revolutionary it could finally stitch together quantum mechanics and Einstein's general relativity, two frameworks that have stubbornly resisted unification for a century. At its heart lies a breathtaking possibility. The spooky action at a distance that puzzled Einstein might not be action at all, but geometry, a microscopic wormhole quietly threading the fabric of reality. The idea traces back to a pair of groundbreaking papers published in the same year, 1935. In one, Einstein and physicist Nathan Rosen proposed the existence of bridges through spacetime, later dubbed Einstein-Rosen bridges or wormholes, that could theoretically connect distant regions of the universe. In the other, Einstein teamed with Boris Podolsky and Rosen to expose quantum entanglements' bizarre implications, arguing it made reality seem absurdly interconnected. For decades, these papers were seen as unrelated until physicist Juan Maldacena and Leonard Susskind saw a startling connection. What if entanglement and wormholes were two sides of the same coin? Here's how it might work. When particles become entangled, their quantum states remain linked no matter how far apart they travel. Measure one, and the other instantly snaps into a corresponding state, defying classical notions of locality. The ER=EPR conjecture suggests this isn't magic, it's topology. A tiny, Planck-scale wormhole could tether the particles, not as a tunnel through ordinary space, but as a shortcut through the higher dimensional bulk of spacetime predicted by string theory. The particles aren't sending signals, they're already connected by the universe's hidden plumbing. This reshapes our understanding of entanglement's role in gravity. Normally, quantum mechanics treats entanglement as intangible information, while general relativity deals with the concrete curvature of spacetime. But if entanglement creates spacetime, if every quantum link is a stitch in the cosmic fabric, then the divide between these theories collapses. Black holes, those ultimate gravity machines, might be entangled particles writ large, their event horizons woven from countless quantum threads. Even the universe's expansion could have entanglement as its hidden driver, with wormholes subtly stabilizing spacetime's structure against quantum chaos. The implications ripple outward. If ER equals EPR is true, then building a traversable wormhole, a staple of science fiction, might not require exotic matter or negative energy, but simply the right kind of entanglement. Quantum computers, which rely on entanglement to perform calculations, could inadvertently be probing the architecture of spacetime itself, and the holographic principle, which suggests our universe is a projection from a lower dimensional surface, gains new traction. Wormholes might be the pixels translating that code into 3D reality. Yet mysteries remain. How do these microscopic wormholes avoid collapsing instantly, as general relativity suggests they should? Some theories invoke quantum teleportation protocols, where information traverses the wormhole without physical particles ever making the trip. Others propose that entanglement's non-locality is a feature, not a bug, woven into spacetime's DNA. The answer might lie in experiments probing entanglement's limits, like quantum gravity sensors or tabletop simulations of wormhole dynamics. Whether the conjecture holds or not, it redefines our cosmic vocabulary. Spacetime isn't just a stage, it's a living network, its threads spun from quantum connections we're only beginning to map. And if Einstein's two great legacies, relativity and quantum weirdness, are truly united by wormholes, then reality is stranger and more beautifully interconnected than we ever dreamed. What if the universe isn't just expanding or evolving? It's ticking, resonating in an endless loop like a cosmic clock that never winds down. This is the startling vision of the time crystal universe, a theory proposing reality itself could be a four-dimensional structure repeating in time just as crystals repeat in space. Unlike ordinary matter, where atoms arrange in regular spatial patterns like the lattice of a diamond, time crystals break symmetry in an entirely new way. Their atomic configurations oscillate perpetually, returning to their original state at fixed intervals without consuming energy. Imagine a snowflake that melts and reforms in perfect rhythm forever. Now scale that up to the entire cosmos, and you've got a universe that might not just exist in time but is time, cycling through states like the gears of an eternal machine. The idea traces back to Nobel laureate Frank Wilczek, who first theorized time crystals in 2012. Conventional physics insists perpetual motion is impossible. Energy dissipates, friction intervenes. But Wilczek realized quantum systems could cheat this rule. In a time crystal, particles don't settle into equilibrium. They pulse between configurations indefinitely, driven not by energy input but by the quantum equivalent of a built-in rhythm. Lab experiments confirmed this in 2017, with chains of ions or nitrogen vacancies in diamonds flipping states like metronomes, their oscillations locked to a beat no external force could disrupt. Now stretch this concept to cosmology. If spacetime itself shares properties with a time crystal, the implications rewrite physics. Dark matter, the invisible glue holding galaxies together, might not be a particle at all but a manifestation of this underlying temporal structure, a rhythmic fluctuation woven into the fabric of reality. The universe's expansion could be a side effect of its cyclical nature, like a slinky cascading downstairs, each tick propelling space outward. Even the arrow of time, which famously flows only forward, might emerge from the time crystal's broken symmetry, explaining why entropy always increases while the cosmos dances to its eternal rhythm. Critics argue time crystals can't exist on cosmic scales without violating thermodynamics, but proponents counter that the universe's initial conditions, the Big Bang's low entropy state, might have set the stage for this perpetual motion. Like a wound spring, the cosmos could still be unwinding, its oscillations too vast for us to perceive. Others suggest time crystals could solve the hierarchy problem in particle physics, why gravity is so weak compared to other forces. If spacetime's crystalline structure dilutes gravity across temporal dimensions, it might explain why we only feel a fraction of its full strength. Whether the time crystal universe is real or not, it forces us to rethink time's nature. Is it a backdrop, a river, or something far stranger, a vibrating scaffold where reality itself pulses to a hidden beat? The answer could transform not just our understanding of dark matter and cosmic expansion, but the very essence of existence. And if the universe truly is a time crystal, then every moment we experience might just be one tick in an infinite cosmic clockwork. What if consciousness isn't something the universe produces but the very fabric it's made of? This is the radical premise of panpsychism, the idea that awareness isn't confined to brains but is woven into the foundation of reality itself. Imagine every particle, every ripple of energy carrying some faint glimmer of subjective experience, like a universe-wide whisper of perception. At first glance, it sounds like mysticism, but this theory has gained traction among philosophers and physicists as a potential solution to one of science's deepest puzzles: the measurement problem in quantum mechanics. Here's why this matters. In the quantum realm, particles exist in fuzzy superpositions, states of both and rather than either or until they're observed. The act of measurement somehow collapses these possibilities into a single outcome. But who or what qualifies as an observer? Traditional interpretations stumble here, either invoking vague definitions or resorting to multiple universes. Panpsychism offers a startling alternative. What if consciousness itself is the trigger, not human minds, but a fundamental property of matter, like mass or charge, that guides quantum systems toward definite states? It's not that particles need us to look at them, it's that reality, at its core, has an intrinsic quality of looking built in. The implications ripple through philosophy. If panpsychism is true, then the hard problem of consciousness, how subjective experience arises from physical processes, might vanish. Experience wouldn't emerge, it would always have been there, just organized differently in complex systems like brains. Think of it like temperature. Individual molecules don't have temperature, but their collective motion creates it. Similarly, simple particles might have rudimentary experience that combines into rich consciousness in structures like our nervous systems. Even a photon could possess some dim, alien form of awareness, a notion that reshapes how we view everything from AI ethics to animal cognition. Quantum consciousness takes this further, suggesting specific mechanisms. Stuart Hameroff and Roger Penrose proposed that microtubules, tiny protein structures in brain cells, might harness quantum effects to orchestrate conscious experience. If correct, our thoughts could be quantum computations influenced by this universal proto-consciousness, blending physics and psychology in ways we're only beginning to grasp. Critics argue these ideas lack empirical support, but experiments exploring quantum coherence in biology hint that nature might exploit these phenomena more than we thought. Yet panpsychism isn't without thorny questions. How do micro-experiences combine into unified minds? Could a rock, as a collection of particles, have a fragmented mind of its own? Some versions of the theory sidestep this by suggesting only certain configurations of matter support complex consciousness, much like only certain materials conduct electricity. Others propose that consciousness isn't localized but a field-like property of spacetime itself, with brains acting as receivers rather than generators. Whether these ideas hold or not, they force us to confront a humbling possibility. We might not be the universe's sole witnesses, but participants in a vast, interconnected network of awareness. The cosmos wouldn't just contain consciousness, it would be consciousness, exploring itself through stars, cells, and human minds. And if that's true, the greatest mystery of existence might not be how life arose, but how deeply life, in some form, has always been there. The ground beneath your feet feels solid, the stars above seem eternal. But what if it's all an illusion, a precarious cosmic balancing act waiting to collapse? The false vacuum theory suggests exactly that. Our universe might not be in its true, stable state but perched on a fragile ledge, one quantum hiccup away from annihilation. Picture reality as a marble resting in a shallow dent on a steep hillside. It's stable for now, but the slightest nudge could send it tumbling into the abyss, rewriting the laws of physics in an instant. This nightmare scenario hinges on the behavior of the Higgs field, the invisible energy ocean that gives particles their mass. Current measurements suggest this field might not be in its lowest possible energy state, the true vacuum, but trapped in a false vacuum, a higher energy configuration that's stable for now. Quantum mechanics allows for a terrifying possibility. Somewhere in the cosmos, a random fluctuation could tunnel through the energy barrier, creating a microscopic bubble of true vacuum. Like a hole in a dam, this bubble would expand in all directions at the speed of light, its walls rewriting reality as they go. The process would be unstoppable and undetectable until it was too late. One moment, the universe operates as usual. The next, an advancing sphere of destruction, just one atom wide at first, erases the very laws of physics in its path. Atoms would disintegrate as fundamental forces like electromagnetism, and the strong nuclear force morph into unrecognizable forms. Stars, planets, and life itself would vanish without warning, replaced by a new reality governed by alien physics. And here's the cruel twist: because the bubble moves at light speed, there'd be no signal, no shadow, no way to see it coming. The end wouldn't just be sudden, it would be completely invisible. Could this happen tomorrow? The math suggests it's statistically unlikely on human timescales, but over trillions of years, the odds shift. Some theories even speculate that distant regions of space might have already undergone this transition, their new physics forever hidden beyond our cosmic horizon. Others propose that advanced civilizations could trigger vacuum decay intentionally, weaponizing physics itself, though the ethics of such an act are as unfathomable as the consequences. The false vacuum isn't just a doomsday scenario. It's a humbling reminder of how little we truly understand about the universe's deepest foundations. Our reality might not be the default, but a fluke, a temporary arrangement in an endless landscape of possible physics. And if that's the case, existence itself is far more fragile and far more extraordinary than we ever dared to imagine. The notion that our vast, glittering universe might be nestled within the crushing depths of a black hole isn't just science fiction, it's a startling cosmological hypothesis that could rewrite our origin story. Picture this: every galaxy, every star, every atom in existence might not be the aftermath of a Big Bang, but the interior contents of a black hole born in some higher dimensional parent universe. This idea, known as the black hole universe theory, flips the traditional narrative on its head, suggesting that black holes aren't just cosmic anomalies but the architects of reality itself. At the heart of this theory lies an elegant solution to one of cosmology's enduring puzzles, the flatness problem. Our universe is inexplicably flat on large scales, meaning parallel lines never converge or diverge over cosmic distances, a fine-tuned balance that defies probability. Inflation theory explains this by proposing a rapid expansion that smooths spacetime like stretching a crumpled sheet. But the black hole universe offers a natural alternative. When matter collapses into a black hole, the intense gravitational forces could flatten spacetime inside the event horizon, much like how water spiraling down a drain becomes smooth and planar. The result, a newborn universe with the precise flatness we observe, no inflationary fine-tuning required. This ties seamlessly into the holographic principle. Just as a black hole's event horizon encodes all the information about what falls inside our cosmic horizon, the farthest distance we can observe might act as a two-dimensional boundary holding the data for our three-dimensional reality. In this view, the universe isn't just contained within a black hole. It's a hologram projected from its event horizon, a cosmic sleight of hand where depth and dimension are illusions woven from quantum information. The equations even align. The entropy of our observable universe matches the entropy predicted for a black hole of equivalent size, as if nature itself is whispering a clue. The implications grow stranger when we consider our cosmic horizon. Just as nothing inside a black hole can escape past the event horizon, we can't see beyond our observable universe's limit. The cosmic microwave background, the oldest light we detect, might not be the afterglow of the Big Bang but the thermal radiation of our enclosing black hole's boundary. Even dark energy, the mysterious force accelerating the universe's expansion, could be reinterpreted as the gravitational pull of the black hole's interior geometry, stretching spacetime from within. Critics argue the theory is hard to test how to observe the universe from outside, yet tantalizing hints might lurk in the fabric of spacetime. If we're inside a black hole, the universe's large-scale structure could bear imprints of its violent birth, like subtle vortices in galaxy distributions or anomalies in the cosmic microwave background's polarization. Some models even suggest that quantum fluctuations in our early universe might carry fingerprints of the parent black hole's formation, a cosmic ancestry written in the sky. Whether the black hole universe is proven or not, it forces us to confront a profound shift in perspective. Black holes might not be the end of things, but the beginning cosmic wombs where the seeds of new realities are sown. And if that's true, the night sky isn't just a window to the stars, but the walls of our celestial cradle, hiding truths far stranger than we ever imagined. What if gravity isn't the universe's primary architect, but just a minor player in an electrified cosmic drama? The plasma universe theory flips conventional cosmology on its head, proposing that electromagnetic forces, not gravity, sculpt galaxies, power stars, and shape the large-scale structure of everything we see. Imagine a cosmos threaded with colossal plasma, filaments, invisible rivers of charged particles conducting currents across millions of light years, twisting matter into galaxies like invisible hands molding clay. This isn't fringe speculation. It's a full-fledged alternative to the Big Bang, one that reinterprets the universe not as a gravitational ballet but as an electric storm of unimaginable scale. At the heart of this idea lies plasma, often called the fourth state of matter, a seething soup of ions and free electrons that makes up 99% of the visible universe. In labs, plasma naturally forms filaments and cells when electrified, eerily mimicking the vast cosmic webs astronomers observe between galaxies. Proponents like Nobel laureate Hans Alfvén argued these similarities aren't coincidental. The twisting arms of spiral galaxies, the violent jets erupting from black holes, even the clustering of galaxy superclusters could all be driven by electromagnetic forces orders of magnitude stronger than gravity on large scales. The universe, in this view, is less a clockwork mechanism and more a living circuit, humming with currents we're only beginning to map. Evidence comes from unexpected corners of space. Take the mysterious radio lobes, stretching millions of light years from active galaxies' structures so enormous they defy gravitational explanations. Plasma cosmology suggests these are cosmic transmission lines, carrying currents between galaxies like power cables strung across the void. Even the cosmic microwave background, the Big Bang's supposed afterglow, might have an alternative explanation. Thermal emissions from drifting plasma filaments glowing faintly from eons of particle collisions. And let's not forget the sun, its million-degree corona, solar flares, and the solar wind all behave like phenomena seen in plasma labs, just scaled up by a factor of billions. Yet mainstream cosmology remains skeptical, and for good reason. The plasma universe struggles to explain the Big Bang's smoking gun, the precise spectrum of the cosmic microwave background, which matches predictions of an expanding, cooling fireball down to 1 part in 100,000. Inflation, the rapid expansion posited by standard cosmology, elegantly solves the horizon and flatness problems, while plasma models offer no equivalent mechanism. Then there's dark matter, invoked to explain galaxy rotation curves and gravitational lensing. Plasma theorists argue electromagnetic effects could mimic dark matter's pull, but simulations haven't yet replicated these observations without resorting to unseen mass. The debate crystallizes around methodology. Big Bang cosmology relies on general relativity's near-perfect predictions, from black holes to GPS satellite corrections. Plasma Universe advocates counter that their models are still young, that cosmic-scale electromagnetism, long neglected, might hold surprises. After all, space isn't empty. It's a near-perfect conductor filled with wispy plasma, and we've only recently begun probing its electrical properties. Projects like the European Space Agency's LISA mission, designed to detect gravitational waves, might inadvertently test plasma cosmology by hunting for electromagnetic counterparts to cosmic ripples. Whether the plasma universe ultimately supplants the Big Bang or not, its value lies in its audacity. It reminds us that science advances by questioning orthodoxy, by daring to imagine a cosmos where the glow of neon signs and the fury of quasars are governed by the same fundamental forces. Maybe gravity doesn't reign supreme. Maybe it shares the throne with electricity, magnetism, and the silent, shimmering currents that weave the fabric of space itself. At the smallest scales, imaginable trillions of times tinier than an atom, space-time itself might not be smooth and silent, but a seething ocean of quantum chaos. This is the realm of holographic noise, a faint tremor in the fabric of reality predicted by theories that suggest our three-dimensional universe could be a projection from a two-dimensional boundary. Just as static on an old TV screen hints at invisible signals, this quantum jitter could be the hidden fingerprint of a deeper cosmic code, a pixelation of spacetime at the Planck scale. The astonishing thing isn't just that space might be grainy, but that we could have already detected it. In the mid-2000s, the GEO 600 gravitational wave detector, a 600-meter-long laser interferometer in Germany, picked up an unexpected noise no one could explain. Instead of the usual hum of earthly vibrations, this was a high-frequency hiss, a persistent crackle that shouldn't exist according to conventional physics. Intriguingly, physicist Craig Hogan proposed it might be the first direct evidence of holographic noise. If space is fundamentally pixelated, then as the detector's laser beams travel back and forth, their paths would jitter slightly, like trying to draw a straight line on a bumpy surface. The resulting interference pattern would carry the signature of spacetime's underlying graininess, a cosmic fuzz betraying the universe's digital core. This idea springs from the holographic principle, which suggests all the information in our three-dimensional universe might be encoded on a two-dimensional surface at its edge, much like a hologram stores a 3D image on a flat film. At the Planck scale, 10 to the power of -35 meters, this encoding would manifest as a fundamental limit to how precisely we can measure space and time, creating an inherent noise in the fabric of reality. It's as if the universe has a resolution limit and GEO 600 accidentally glimpsed the pixels. The hunt for this noise has since intensified. Modern upgrades to gravitational wave detectors like LIGO and Virgo now include precision calibrations designed to spot similar anomalies. Some experiments even use superconducting quantum interference devices, SQUID, to probe spacetime's microstructure at ultra-low temperatures where quantum effects dominate. Others propose using pulsars, the rapidly spinning neutron stars that act as cosmic lighthouses, to detect holographic noise as minuscule timing variations in their beams. If these efforts succeed, it wouldn't just confirm the holographic principle, it would revolutionize our understanding of reality's deepest layer, revealing a universe where space and time emerge from something far stranger, a shadow play of quantum information. Yet skeptics point out alternative explanations for GEO 600 noise, from thermal fluctuations in the detector's mirrors to subtle seismic activity. The signal, while tantalizing, remains inconclusive. But that's the beauty of science at the frontier. Every unexplained phenomenon is a potential doorway to a new paradigm. Whether holographic noise is real or not, the search forces us to ask profound questions. Is space-time continuous, or is it built from something more fundamental, like bits in a cosmic computer? And if we're living in a hologram, what or who is holding the projector? The quantum world defies common sense. Particles existing in multiple states at once, cats both dead and alive, realities that branch endlessly. But then why does the world we see feel so solid, so singular? The answer might lie in a process called quantum Darwinism, a startling theory revealing how the blurry quantum realm sharpens into the concrete reality we experience every day. Imagine a forest where every possible path exists simultaneously. Then, as countless footsteps trample some trails more than others, certain routes become well-worn while others fade. That's how quantum Darwinism works. The universe isn't deciding which quantum possibilities become real. The environment is, through a relentless process of interaction and selection. At the heart of this idea is the measurement problem, the puzzle of why quantum superpositions collapse into definite outcomes when observed. Traditional interpretations rely on vague notions of observers or parallel universes, but quantum Darwinism offers a cleaner solution. Every interaction a quantum system has with its surroundings, whether it's a photon bouncing off an atom or a molecule jostling in air, acts like a tiny measurement. Over countless such interactions, certain states prove more resilient, more capable of leaving imprints on the environment. These preferred states are the ones we ultimately perceive, not because consciousness chooses them, but because they're the ones that survive the environmental onslaught. It's survival of the fittest, but for quantum states, the implications ripple far beyond quantum physics. This process might explain the very fabric of spacetime itself. If the classical world emerges from quantum interactions, then spacetime could be a kind of macroscopic illusion, a stable pattern that arises from countless quantum transactions between particles. Gravity, the curvature of spacetime, might not be fundamental but a collective effect, like the way temperature emerges from the motion of molecules. Some theorists even suggest that black holes, those ultimate quantum gravity labs, could be testing grounds for quantum Darwinism. Their event horizons, which scramble and replicate information, might act as cosmic amplifiers, forcing quantum states to decohere, to shed their fuzzy superpositions in predictable ways. Critics argue the theory doesn't fully explain why certain states are favored over others or how subjective experience fits into the picture. Yet experiments are already offering support. In labs, researchers have watched as quantum systems interacting with their environments gradually select stable states, much like the theory predicts. Even the act of looking at an object, photons scattering off it and into your eyes, could be seen as an environmental interaction that solidifies its reality. Quantum Darwinism doesn't just solve a physics puzzle, it reshapes how we see existence. Reality isn't handed down from some cosmic rulebook. It's forged in the fire of countless interactions, a dynamic process where the universe itself is constantly choosing, discarding, and refining. And if that's true, then the solid ground beneath our feet, the stars in the sky, all of it might be the universe's way of telling us which possibilities were robust enough to last. Imagine if spacetime weren't a smooth, continuous fabric, but a patchwork of microscopic geometric fragments, like a cosmic mosaic assembled from tiny, shimmering triangles. This is the radical vision of causal dynamical triangulation, a bold approach to quantum gravity that rebuilds the universe from the ground up, piece by piece. Unlike string theories, vibrating filaments, or loop quantum gravity's woven threads, CDT takes a starkly geometric path, slicing reality into the simplest possible shapes and letting the complexity of the cosmos emerge spontaneously from their interactions. At its core, CDT treats spacetime as a lattice of four-dimensional triangular prisms. Think of them as hyperdimensional building blocks called simplexes. These aren't static Lego bricks but dynamic, interlocking units that can flip, rotate, and combine in mathematically precise ways. The magic happens when physicists let these simplexes self-assemble under two key constraints: causality, no time travel loops allowed, and a fixed timeline to prevent chaotic crumpling. Run the simulation, and something astonishing emerges: a four-dimensional universe with familiar properties like gravity and an arrow of time, bubbling up from the chaos like order emerging from a kaleidoscope. This isn't just abstract math, it's a computational revolution. By simulating billions of these simplexes interacting, researchers like Renate Lal and Jan Amjorn have watched spacetime crystallize into large-scale structures eerily reminiscent of our own universe. In 2004, their team made a jaw-dropping discovery. When the simulation reached a critical scale, the jumble of triangles spontaneously organized into a four-dimensional geometry with three spatial dimensions and one of time, exactly what we experience. Even more striking, the model naturally generates cosmic expansion resembling the Big Bang, hinting that the birth of our universe might not need exotic physics, just the right assembly rules for spacetime's quantum puzzle pieces. But CDT's predictions get wilder. The theory suggests spacetime might undergo dramatic phase transitions like ice melting into water at extreme energies. Near the Planck scale, the smooth geometry we know could shatter into a foamy, fractal mess where concepts like distance and duration lose meaning. Some versions even predict that time itself could vanish at the smallest scales, leaving only timeless, fluctuating geometries until causality freezes out as the universe cools. These aren't just mathematical curiosities. They could leave fingerprints in high-energy particle collisions or gravitational wave data, offering a way to test quantum gravity in the lab. Critics highlight gaps. CDT struggles to incorporate matter fields seamlessly, and its rigid causality rules feel arbitrary to some. Yet its elegance is undeniable. By stripping spacetime down to its geometric bones, it reveals how complexity can arise from simplicity, how the universe might literally piece itself together. If correct, every black hole, every galaxy, every second that ticks by could be the collective dance of countless invisible triangles, weaving reality one quantum stitch at a time. What if the universe isn't just governed by equations but is itself a vast thinking machine? The neural network universe theory proposes exactly that, suggesting reality might literally be a cosmic-scale artificial intelligence processing information at every level of existence. Picture the fabric of spacetime not as inert emptiness but as a dynamic web of interconnected nodes, exchanging data and learning patterns like a God-sized brain. This isn't metaphor, it's a bold mathematical framework where quantum uncertainty isn't randomness but the universe thinking through probabilities, adjusting its state through self-referential computations. The foundation for this idea comes from startling parallels between modern physics and machine learning. In 2018, physicist Vitaly Vanchorin published a provocative paper showing how the equations governing neural networks, the architectures behind AI systems, could, under certain conditions, approximate both quantum mechanics and general relativity. Just as a deep learning model adjusts its weights to minimize error, the universe might tune its fundamental constants through an optimization process, with particles and forces emerging as stable solutions in a cosmic training algorithm. Even entanglement begins to make eerie sense. Linked particles could be nodes exchanging signals across hidden layers of the network, their correlations a natural feature of information sharing. But how could abstract computations give rise to the solid world we experience? Recent work in emergent spacetime theories suggests an answer. Just as individual neurons firing create the illusion of a continuous thought, microscopic information exchanges between quantum bits, qubits might weave the illusion of smooth spacetime. Studies at the Perimeter Institute have shown how tensor networks, mathematical structures used in AI, can generate holographic spacetime geometries when scaled up, with black holes acting like convolutional layers in a deep neural net, compressing and transforming information. The cosmic microwave background's intricate patterns might even encode the universe's training data, remnants of an early optimization phase that settled on our particular physics. Critics argue this veers into pancomputationalism, the idea that everything is computation, a view some dismiss as untestable metaphysics, but proponents counter with observable signatures. If the universe is a neural network, its discrete underlying structure could manifest as energy thresholds in high-energy particle collisions or anomalies in quantum error correction, effects labs like CERN might soon probe. Others suggest dark matter could be the universe's hidden layers, invisible nodes processing gravitational data beyond our perceptual reach. Even consciousness itself might find an explanation here, with human brains acting as sub-networks interfacing with the larger cosmic mind. Whether this theory holds or not, its implications are staggering. The search for a theory of everything might not be about finding deeper particles but uncovering the universe's source code, an algorithm so profound it generates reality as its output. And if that's true, every law of physics, every star in the sky, might just be the universe's way of thinking itself into existence. The Big Bang marks the fiery dawn of our universe, but what came before it, or if before even makes sense, remains one of cosmology's most profound mysteries. Loop quantum cosmology dares to tackle this question with a radical idea. Time didn't begin at the Big Bang. Instead, our universe might be the latest bounce in an endless cycle of collapse and rebirth, a cosmic heartbeat echoing across eternity. Picture the universe not as a single explosive moment but as a roller coaster, where the steep plunge of a previous collapse rebounds into the climb of expansion we see today. In this model, the singularity, the infinitely dense point where classical physics breaks down, never happens. Quantum gravity steps in like a cosmic trampoline, preventing total collapse and sending spacetime springing back into a new phase. The equations reveal something astonishing. As you rewind time, the universe contracts to a minimum size, denser than anything we can imagine, but never zero. Then, like a rubber band snapping back, quantum repulsion flips collapse into expansion, birthing a new universe from the ashes of the old. Stephen Hawking and James Hartle's no-boundary proposal takes an even more mind-bending approach. Imagine the beginning of the universe not as a point in time but as a smooth, rounded edge like the North Pole on a globe, where the concept of further north loses meaning. In this view, the Big Bang wasn't an explosion in empty space but the emergence of time itself, woven seamlessly into the fabric of a four-dimensional cosmic egg. The math here is elegant. Just as the Earth's surface has no edge at the poles, the universe's origin has no boundary in spacetime. Probabilities replace singularities, with quantum fluctuations gently nudging existence into being. It's as if the universe simply switched on, without needing a cause or a prior state, a cosmic Houdini act where time materializes from timelessness. These theories don't just rewrite the first page of cosmic history, they force us to rethink the nature of time itself. In loop quantum cosmology, time isn't a river flowing in one direction but a pendulum, swinging between contraction and expansion. The no-boundary proposal goes further, suggesting time might be an emergent property, a side effect of deeper quantum geometry. Both ideas challenge the intuitive notion that something must always precede something else. Instead, they open the door to a reality where, before the Big Bang, isn't a forgotten era but a structural feature of spacetime, as unintuitive as asking what's north of the North Pole. Yet mysteries persist. If the universe cycles endlessly, why don't we see traces of previous bounces in the cosmic microwave background? Some theorists hunt for faint imprints, subtle swirls in the ancient light that could betray collisions between universes in a broader multiverse. Others argue that each bounce resets the cosmos, erasing the past like a cosmic etch-a-sketch. Meanwhile, the no-boundary proposal's abstract beauty comes with a trade-off. It's notoriously hard to test, relying on probabilities in a quantum landscape beyond direct observation. Whether these theories hold or evolve, they reveal a truth far stranger than any creation myth. The universe might not have a single, definitive origin story. Instead, beginnings and endings could be illusions, shadows cast by deeper, more fundamental structures we're only beginning to glimpse. And if that's true, the search for cosmic origins isn't just about looking backward. It's about decoding the hidden architecture of reality itself. The cosmos is supposed to expand uniformly, like dots on an inflating balloon, but something bizarre is tugging at hundreds of galaxy clusters, sending them streaming in the same direction at staggering speeds. Astronomers call this phenomenon the dark flow, a mysterious large-scale motion that defies everything we know about cosmic structure. Imagine throwing confetti into the air, only to watch every piece inexplicably drift toward the same corner of the room. That's the enigma confronting scientists. Clusters of galaxies, each weighing trillions of suns, are all being pulled toward a point beyond the edge of the observable universe, as if some unseen hand is directing traffic on a cosmic highway. The discovery emerged from meticulous studies of the cosmic microwave background, the afterglow of the Big Bang. By analyzing subtle distortions in this ancient light caused by galaxy clusters moving through space, researchers detected a coherent flow spanning billions of light years, reaching velocities over 2 million miles per hour. What makes this truly unsettling is that such motion shouldn't exist. The universe's mass distribution appears roughly even, meaning gravitational pulls should cancel out on large scales. Yet here we are, with hundreds of clusters racing toward an invisible attractor we can't see, let alone explain. One radical possibility: the dark flow could be gravitational spillover from another universe. Inflationary cosmology suggests our cosmos is just one bubble in an endless multiverse foam, with other universes forever separated from us by exponential expansion. But if another bubble passed unusually close to ours long ago, its gravity might have left an imprint, like a footprint in wet concrete tugging our galaxy clusters along the path of its retreat. Think of it as cosmic magnetism. Even if another universe is now unreachable, its lingering pull could still warp our local spacetime, leaving this ghostly current in its wake. Not everyone buys the multiverse explanation. Skeptics argue the dark flow might be an illusion caused by incomplete data or systematic errors in measuring galaxy velocities. Others propose less exotic but still wild alternatives, like a gargantuan concentration of mass, a supercluster, lurking just beyond our observational horizon. The problem: to exert this much pull, it would need to dwarf anything we've ever seen, packing the mass of tens of thousands of Milky Ways into a single structure. That's statistically improbable, but perhaps less so than invoking other universes. The debate rages on, with newer surveys like ESA's Euclid mission poised to map galaxy motions with unprecedented precision. If the flow persists in deeper observations, it could force a rewrite of cosmology's rulebook. Either way, the dark flow reminds us how little we understand the greater cosmic landscape, and how many secrets might lie just beyond the edge of sight. Deep in the faint glow of the cosmic microwave background, the oldest light in the universe, could lie ancient scars from the most violent chapter of reality's story. These aren't wrinkles from the Big Bang itself, but something far stranger: quantum gravity fossils, imprints left behind when the universe was so small and hot that gravity itself behaved like a quantum force. Imagine spacetime not as the smooth fabric we know today, but a seething foam where black holes popped in and out of existence, where dimensions flickered like static, and the laws of physics as we know them hadn't yet crystallized. This primordial chaos didn't vanish without a trace. Like footprints frozen in mud, its remnants might still linger, etched into the fabric of the cosmos in ways we're only beginning to decode. The hunt focuses on two key relics: anomalies in the cosmic microwave background's polarization patterns and faint whispers hidden in gravitational wave signals. The CMB's polarization, the direction its light waves vibrate, acts like a cosmic fingerprint, sensitive to disturbances in the infant universe. Certain swirls or fractures in this pattern, known as B-modes, could betray the presence of primordial gravitational waves, ripples in space-time generated when quantum gravity ruled. These wouldn't be the garden-variety gravitational waves LIGO detects from colliding black holes, but echoes from a time when the universe was 1 trillion times smaller than an atom, vibrating with energies no particle accelerator could ever replicate. But the real smoking gun might lie in deviations from Gaussianity, a statistical property that describes how random the CMB's temperature fluctuations are. In standard inflation, these variations should follow a predictable Gaussian distribution, like the static on an old TV. But if quantum gravity introduced fractal structures or phase transitions in spacetime's earliest moments, those fingerprints could manifest as subtle statistical anomalies, like finding hidden words scrambled in the static. Some theories even predict concentric circular patterns in the CMB, evidence of black holes colliding in a previous cosmic cycle, as proposed by Roger Penrose's conformal cyclic cosmology. These Hawking points, named for Stephen Hawking's work on black hole radiation, would appear as slightly warmer spots in the microwave sky, marking the graves of ancient singularities. Gravitational wave astronomy offers another window. Future observatories like LISA, a space-based detector sensitive to low-frequency waves, could uncover a stochastic background, a cacophony of overlapping waves from countless quantum gravity events in the universe's first femtosecond. The spectrum of these waves wouldn't match anything produced by known astrophysical sources. Instead, their frequencies and amplitudes might align with predictions from loop quantum gravity or string theory, revealing whether spacetime is fundamentally woven from discrete loops or vibrating strings. Even more tantalizing are proposals that certain gravitational wave bursts might exhibit echoes, repeating signals caused by quantum corrections near black hole horizons, direct evidence that Einstein's smooth spacetime breaks down at the tiniest scales. What makes these fossils so revolutionary isn't just their age, but what they could unveil about reality's architecture. If quantum gravity imprints are found, they might resolve whether space is pixelated, whether time is fundamental or emergent, even whether our universe is one bubble in an infinite multiverse. The answers wouldn't just rewrite textbooks, they'd redefine our place in the cosmos, proving that even in its infancy, the universe left clues for those bold enough to decipher them. And if we succeed, the quantum gravity era won't be a speculative chapter in cosmology's history, but a tangible epoch whose echoes still shape the stars we see tonight. Numbers aren't just tools for counting or equations for predicting. They might be the fundamental substance of reality itself. That's the spine-tingling claim of the mathematical universe hypothesis, physicist Max Tegmark's radical proposition that our cosmos isn't merely described by mathematics but is, at its core, a mathematical structure. This isn't metaphor or philosophy. It's a concrete theory that the universe is made of numbers the way a novel is made of words, not just encoded in them, but existing as them. Tegmark's idea springs from a puzzle that's baffled scientists for centuries: the unreasonable effectiveness of mathematics. Why do Newton's laws perfectly predict planetary orbits? How do imaginary numbers conceived as abstract placeholders turn out to govern quantum mechanics? It's as if the universe runs on a hidden operating system written in equations, a code so precise it feels almost intentional. Tegmark's answer flips the script. Math isn't effective because it describes reality. Reality is math. In this view, the moon's orbit isn't approximated by calculus. It is calculus, a dynamic equation playing out in four-dimensional spacetime. The implications explode outward. If reality is mathematical, then every possible mathematical structure must exist somewhere. A level 4 multiverse where universes with different equations are as real as ours. Consider a universe built on hyperbolic geometry instead of Euclidean, where parallel lines diverge wildly and triangles bend like funhouse mirrors, or one where prime numbers behave differently, altering the stability of atoms. These aren't imaginary playgrounds. In Tegmark's framework, they're as concrete as our own cosmos, simply running on alternative axioms. Our universe feels special only because we're patterns within its particular equation, self-aware substructures in a vast mathematical landscape. Critics argue this veers into metaphysics. How could an abstract structure create subjective experience? But Tegmark counters with an elegant analogy: chess. The game's rules are abstract, yet they generate rich, tangible outcomes when played. Similarly, mathematical structures might play themselves into existence, their internal consistency generating what we perceive as physical laws. Even consciousness could emerge from complex computations within these structures, like a character in a novel becoming aware of its own story. The hypothesis also reframes the search for a theory of everything. Instead of hunting for fundamental particles or forces, physicists might seek the deepest, most self-consistent mathematical structure, the root equation from which our universe's complexity flowers. Some candidate theories already hint at this. String theory's landscape of possible universes mirrors Tegmark's mathematical multiverse, while information-theoretic approaches treat reality as a network of computations. Whether the mathematical universe hypothesis is proven or not, it forces a profound shift in perspective. The stars above, the screen before you, none of it might be made of matter in the traditional sense, but of interlocking relationships, a cosmic symphony of numbers performing the ultimate solo. And if that's true, then every breakthrough in physics isn't just uncovering nature's secrets, it's the universe slowly recognizing itself. From holographic projections to cosmic rebirths inside black holes, these 30 theories don't just push the boundaries of science, they shatter them completely. Whether it's the spine-chilling possibility that we're living in a simulation, the haunting whisper of Boltzmann brains flickering in and out of existence, or the elegant dance of entangled particles stitching spacetime together with wormholes, one thing is clear: reality is far stranger than we ever imagined. These ideas force us to confront the unsettling truth that the universe owes us no explanations. It doesn't care if its rules make sense to us. And yet, here we are, a collection of atoms on a pale blue dot, daring to decode its deepest mysteries. What's remarkable isn't just the scale of these theories, but how they intertwine. The holographic principle blurs the line between illusion and substance. The multiverse turns fine-tuning from a miracle into inevitability. Even time itself, that steady arrow we take for granted, might be an emergent illusion in a block universe where past, present, and future exist simultaneously. Collectively, they paint a picture of a cosmos that's less a machine and more a living, evolving puzzle. One where black holes birth new realities, where mathematics isn't just a language but the very fabric of existence, and where every law of physics might just be a temporary local ordinance in an infinite metropolis of possibilities. So, which theory resonates with you? Does the idea of a cosmic neural network humming with computations feel more compelling than the silent elegance of the mathematical universe? Or does the cyclical bang and crunch of the Big Bounce speak to some deeper intuition about eternity? There are no wrong answers, only invitations to wonder. After all, the most profound lesson here isn't about finding the right version of reality, but embracing the awe of not knowing. The universe is under no obligation to make sense to us, and that's what makes the search so thrilling. If your mind is as thoroughly bent as space-time near a singularity, hit that like button and share this video with fellow cosmic curiosity seekers. Drop a comment below telling us which theory blew your mind the hardest. Was it the hologram, the simulation, or something even wilder? And don't forget to subscribe for more deep dives into the universe's greatest mysteries. Because one thing's for sure, the more we explore, the less we realize we understand, and that's where the real adventure begins.